Hello, hello. Maybe it's time to start. Well, welcome all of you. It's a great pleasure to see that we can have the De La Pietra lectures with high school students again. During the COVID period, it was almost impossible to bring you here because the controls imposed by the authorities in Long Island made it virtually impossible to have this meeting. This is a set of lectures that are financed by the De La Pietra families who are very interested in disseminating science, especially to young minds like you, which presumably will come and replace me and all the other professors in this building. So maybe some of you, in a few years' time, will come here and do that research. Today's speaker is Alvaro De Rujula. He's one of the pioneers of the standard model of particle physics. He's been working in particle physics, in cosmology, nuclear physics, and all kinds of things. And he's also an excellent communicator of science. So he's going to be telling you about creativity in the arts and the sciences. Please, Alvaro.
Thank you, Luis. And thank you, everybody, for coming or being brought by force. Since I'm a scientist, I don't trust electronics, so I start by doing tests so that I know that things are working. Now, after high school, where you are now, what are you going to do with the rest of your life? Are you going to go to the arts or to the sciences or to medicine or to law or to something else? Whatever your choice is, very soon it will change your brain into something different from what it is now, and you'll view things in a manner that depends on what you decided to do, for instance, at a university. And if you happen to be in Venice and there is someone in a gondola going by, and in red there are three people, one of them is a politician, and the politician would say, perhaps, "Oh, wow, all gondoliers in Venice are women." Now, the artist, being slightly more precise than a politician, would say, no, all that you can say is that that particular gondolier is a woman. And a scientist, particularly a mathematician, for instance, would go even further and say, no, all that you can say is that the left-hand side of that object seems to be a woman. Now, one deep analogy between artists and scientists is something I will talk about for a while, which is their ability to be creative. And that is not an ability of most politicians, alas. Now, here's someone you recognize, Uncle Albert Einstein, and he is pictured here in front of his blackboards. In one of his blackboards, he scribbled this little thing there that looks so mysterious, and it's the theory of general relativity, the theory of gravitation, space, and time. And he even added to it another little piece at a given moment. Now, this theory has always been proved correct with enormous precision, and it describes the orbits of the planets and the properties and existence of black holes and of gravitational waves and the entire expanding universe. The universe is expanding at the moment in an accelerated fashion, which probably has to do with this extra term that Einstein wrote. It is pretty amazing that in such a compact manner you can describe most of the universe. Now let's go to an artist. This is Pablo Picasso in the act of painting one of his most famous paintings, which is called Guernica. Guernica is a town in the north of Spain that was bombarded in 1937 or so by the Nazis, German Nazis, in an attempt to study the effect of bombarding civilians on a war. Instead of bombarding military people, let's try to see what we can do by destroying cities and killing people. And that is now very much something that is going on, as you probably know, so that art can also be political. This painting, so horrible, is a defense by Picasso of the poor people that were bombarded and those that would be bombarded later. Now, one thing that we think that distinguishes apes from people, such as Einstein, is that Einstein could do various things, such as playing the violin, and other people, such as Leonardo da Vinci, perhaps the most renowned artist of all times, is that they share, scientists and artists, a concept of beauty. Beauty for very different things. For instance, scientists think that the equations of relativity that I just showed are very beautiful. And artists think that the Gioconda, for instance, the most famous painting by Leonardo da Vinci, is very beautiful. And presumably monkeys are insensitive to beauty. And that's probably the main reason why we're different from monkeys. And for all of you who are so beautiful. Now, as I just said, a thing that is common to arts and science is that beauty, and scientists think that equations are beautiful for some reason. Now, this is the Gioconda, the most famous painting by Leonardo da Vinci in the Louvre Museum in Paris. And this is one of the thousands of drawings that this same guy, Leonardo da Vinci, made. This is an engineering study of a well or something like that. And he studied all sorts of things and left millions, hundreds of drawings planning different things. For instance, this is supposed to be a helicopter. And he also studied the human body by dissecting it, which was forbidden by the church at the time. So he took a risk in understanding anatomy. Now, Leonardo da Vinci was just educated as a painter's apprentice. And when he had more or less your age, he could not decide what to do next. So he decided he would do everything and became an engineer, a scientist, a poet, a sculptor, a draftsman, an architect, and a few other things. And he managed to encompass all the knowledge of his time, which was possible at that time, even if, like him, even though he did not graduate from an elite American university. And he did not need an MBA from Harvard, for instance, to do all these things. Now, what's the difference between an American university, to which many of you shall, or maybe perhaps all of you, shall soon be going, and a university, for instance, in France? If you go to France, to university, and you study physics, for instance, you study only physics and nothing but physics, and you study it very deeply, and you come out with enormous knowledge of physics. And in an American university, you can concentrate in physics but study very many other things. So someone who has just become a graduate in physics from an American university knows very little physics, because he has studied the wars in Babylonia and lots of other things. And in spite of that, the fraction of people who become great creators of new science, having gone to an American university, is much, much higher than those having gone to a French university, in spite of the fact that the French, at first sight, have a much better education. And the reason for that is that there is still room in the head of someone coming out of an American university for new ideas and for creativity. There's a healthy ignorance, a lack of prejudice, that helps these people be particularly creative. And yo means me. What happened to me when I went to university? Well, I wanted to become like Leonardo da Vinci, studied everything, but didn't learn anything. Now, I don't know why I say creation, that again. Now, this is Leonardo in old age, drawn by himself. And why I insist so much in Leonardo? Well, I have already sort of told you, it's an example to follow because of his breadth of knowledge, but also he was allegedly the winner of the game of creation of all times. Nobody has created so many different things as Leonardo did, with one exception, which is the mother of all creators. Creation is a very ample word and may mean different things. The mother of all creators, in my opinion, is a machine which is in Switzerland, close to Geneva, called the Large Hadron Collider. And it is in a laboratory called CERN. Now, this is an aerial view of the region where this laboratory is. And what you see as a circle is drawn on the picture, and under it, at about 100 meters on average, there is a big collider. I'll tell you what that is in a moment. What you see in the foreground is the airport of the city of Geneva in the west of Switzerland. And above the dotted line, the country is France. Below the dotted line, the country is Switzerland. So the particles that move in the accelerator cross the frontier thousands of times per second. Now, it appears to be all very similar above and below the line of dotted line, which is the separation from France and to Switzerland. However, if you go very precisely closer by where the the right-hand arrow is, for instance, and you look at what is around there, there's an enormous difference between Switzerland and France. And that is, for instance, that in Switzerland, all the houses are like this with gorgeous gardens, beautifully treated. And in France, the gardens are like, in France, they are more or less like that. Nobody cares about having anything well done. So the LHC is at CERN near Geneva in Switzerland. Fermilab is near Geneva, but Geneva, Illinois. And Brookhaven National Laboratory is just around the corner. And all these places have colliders. What is a collider of particles, such as the LHC? It works in the following fashion. You take an atom of hydrogen, which is the simplest chemical element, consists of an electron and a proton. You take the electron out and you inject the proton into a tube where it is electrically accelerated and magnetically guided. And this is what ought to happen now. Here you have a bunch of protons which are boosted to higher energy and then boosted to even higher energy in another circular accelerator. They finally go to a large accelerator where they are brought to even higher energy, and then they are injected into this collider where they move in two different directions at their maximum energy. And this is an artist's view of how the protons are accelerated. They are traveling practically at the speed of light. So this is not a very good rendering. And protons are made of three quarks. They are not elementary particles. They have pieces. And they go in two directions in this collider. And when they collide, if they come on, they collide and puff. The energy that they have is partially converted into things that are created at that moment. Things that did not exist before are made in the act of the collision. Now, this is very different from a usual highway in various senses. It has four crossings where the people going one way and the people going the other way collide. And the other difference is that if you collide two cars in such a stupid highway, what you get are the remnants of the car, the carburetor and the wheels and the hat of the driver and things like that, things that were already there. However, if you collide particles at a sufficiently high energy, you create new things. So unlike in here, here you make things, particles, that were not there before, that you want to study in order to understand the basic laws of nature. And you say, well, that's not so peculiar, because if I have a match and I light it, it's going to emit particles which were not there before, are called photons. Photons of light are emitted when the excited electrons in the flames atoms de-excite themselves by the emission of something that wasn't there before. So this is also an act of creation. But it is an easy act of creation because the mass of the photon is zero. And it is sort of cheap to create something that doesn't have a mass. how do you create things that don't have a mass, that do have a mass? Well, for that, you must remember that Einstein wrote something similar to that, which among other things means that you can convert the energy of the motion of a particle colliding with another one into the mass of new particles that you make as they collide. And that is, at the moment, I'm looking at you, my estimate of the status of the audience at this point in time, when we are halfway through my talk. Now let's go back to the collider, and the same way that Leonardo could do so many things at a time, there are people who are good at least 2 things at a time. For instance, I have a friend who is a scientist. It's not Leonardo, it's someone else, but he draws things exactly the way and the style in which Leonardo drew them. For instance, this is the collider I've been talking about, depicted by this person. And like in Leonardo's paintings and drawings, all the writing is from right to left instead of left to right. So you need a mirror to know what is being said. But in the case of this guy, who is still alive and doing very well, what is written is extraordinarily funny. And so this is the LHC spelled backwards, and this is this guy's name, Sergio Chitolin. And there he is. Now, he also painted many times, when they were being constructed, the detectors with which the results of these collisions are analyzed. This is one of them, and this is it in reality. This is one of the 4 large detectors that analyze the particles made in these very high energy collisions. And to give you an idea of how large these things are, here are a couple of guys in there. This is an enormous, much bigger than this room, maybe twice this room, and it's sort of a sophisticated camera, photo camera. And in a sense, these are the cathedrals of today. People used to get together to build a cathedral, and that would take maybe 50, maybe 100, maybe 300 years. It was an enormous collective effort that implied essentially all the society, and certainly all the artists and constructors, etc., etc. It was an enormous collective effort with a given aim. And these detectors that I have shown you are in a sense the cathedrals of today, because they are also taking, say, 10, 20 years to construct, and enormous amounts of people work in unison to do it with a purpose. The purpose being studying and understanding the fundamental laws of nature. What are we made of, and how the things we are made of behave. In the old times, people would construct cathedrals such as this one in Santiago de Compostela in Spain, and of course put them on the surface for everybody to contemplate. There is a difference with the cathedrals built by scientists, is that our purpose is to increase knowledge, which is not the purpose of the classical cathedrals, and moreover, we scientists are so extremely modest that we build our cathedrals underground. Now, this is a collision between 2 protons about to take place. And you see the blue line on top is a quark that is, my pointer is presumably not working, but I can only point to one of these screens, not two. This quark emits, changes color and emits a gluon, and another gluon from another quark in the other proton coincides with this one, and through a loop of another type of elementary particle called a top quark, they produce a Higgs boson, a new particle recently discovered called the Higgs boson, which on occasion decays again via a loop to 2 different high energy particles of light called photons, as I reminded you. This is so complicated and seems so absurd. And yet what is amazing is that we understand these things very well and can prove that this is really what's going on in the most smallest guts of a proton colliding with another proton. Now, so this is again an act of creation because the Higgs particle wasn't there before you made it. And as I will tell you in a minute, the Higgs particle is very peculiar because, among other things, it is a vibration of the substance of the vacuum. And the other particles, such as a photon, are also vibrations of a substance. The substance in the case of a photon is an electromagnetic field. An electromagnetic field can vibrate and be a particle, which is a photon. Now this is one of these collisions. This is a true one, analyzed by one of these detectors. And it is one of those in which, as in the picture that I showed you before, there appear in the final state, when you take the picture, two particles of very, very high energy, which are photons, emitted more or less one backwards to the other. And this is a picture not of the discovery of the Higgs boson, but of the first collision observed by one of these collaborations. And you can see in this picture that scientists are like the rest of mankind. That is to say, these are the two who worked all the night to make the results possible, and the others are just having fun. You can go to a construction site and see precisely this at any time. And it's not so easy once you have made a Higgs particle and think that you have detected it. There are very many other things that happen that look very much the same. So you have to extract the real signal from the stack, and that takes a lot of doing. And another interesting point that I will mention just in passing is that an elementary particle, such as a Higgs boson, it's called, is completely identical to another one of the same ilk. You have two electrons, they are absolutely identical. They cannot be distinguished, neither in practice nor in any other way. And that's amazing that two things can be so similar. For instance, what are they called in English? Thomson and Johnson, one of them has a mustache that looks like a T and the other one doesn't. So they are not elementary particles because they can be distinguished. Now let's go back to La Gioconda. This was before she went into a heavy duty diet. And you hope it will not burn one day. In fact, it was stolen for many years from the museum and recovered only much later, unlike some things stolen from museums, for instance, in Boston. Now, a Higgs boson that you just have made is, unlike the Gioconda, something that lasts not hopefully forever, but for a tiny fraction of a second, about 10 to the minus 22 seconds in average. So this looks like the most ridiculously useless object you can make, because it lasts a fraction of a second, which is truly, truly tiny. However, the Higgs boson is not irrelevant. First of all, a warning, which is this one that I won't read, because some people call this particle that way. And this is now the status of the audience, 80% through my talk. Now, suppose you had sat in the old-fashioned polite way, so the ladies in front and the guys in the back, and I politely asked you to leave the room, and then I pumped all the air out of the room so that no molecule of anything was left in the room. I took the lights off, and so I covered the room with a shielding that nothing can penetrate. So I made what you would think is a vacuum. I made a piece of vacuum. No, you would say, you haven't succeeded in emptying the room, because if I drop my glasses, they drop. And that means that there remains in this empty room something that you cannot see or touch or smell or feel. No, you can feel it, but you cannot see it with your conventional senses, and that's the Earth gravitational field. So there's a substance in here which I haven't taken out when I thought I took everything out. But now suppose I take the room and I put it in empty space where the gravitational forces in different directions compensate to 0, and then you say, okay, I've made a real vacuum. I made a room full of nothing. However, that is not correct, because there is still something in the room up there, which is the vacuum. And the vacuum is of this particular universe in which we are. The vacuum is a substance. And we express this mathematically by saying that its field, the field of the Higgs field, 0 means in the vacuum, is not 0. So something permeates the universe at all points in space and inside you, which is a substance analogous to a gravitational field, but it is the field of the Higgs boson, and it's constant everywhere. Now, how do we know that such peculiar things, like the statement that the vacuum is not empty, there's no such a thing as a true vacuum in the universe, how do we dare say that these things are correct? And that is the scientific way of proving your statements. In the case of the vacuum and the Higgs field, suppose I have a particle called a muon, and it is sitting or traveling in a vacuum, not truly vacuum because there is Higgs field. Then the interaction between the muon and the field is what produces the mass of the muon. So things that have mass because the vacuum interacts with them. And if that is true, then an excitation of the vacuum, which is the Higgs particle, can decay into particles in a way which is, for instance, a muon, which is a heavy electron and its antiparticle, in a way that is governed by the same amount of interaction between the particle and the vacuum, or the particle and the excitation of the vacuum. So these two blobs in here are proportional to the same mass of a particle. So if I plot the masses of all particles in the horizontal line, and the measured way in which a Higgs boson decays into pairs of those particles, this has to be a straight line, because both things, one is the mass and the other one is linearly proportional in the mass. And you can see here the results of the experiment with very many different particles, thing called a tau, thing called the beauty quark, the W and the Z intermediate vector bosons, the top quark. All these elementary particles fall precisely in that line predicted by the statement that what generates the mass of the particles is their interaction with the field of the vacuum, which now you are totally convinced is not empty, because it does things, such as give you mass. So, from the observed fact that the universe is expanding, that is to say, very distant galaxies are moving away from each other, the space in between them is inflating. But it is not only inflating at a given rate, it is inflating at an accelerated rate. That is to say, tomorrow the universe will be expanding slightly faster than today, because the rate is an accelerated rate. And on the other hand, from the properties of the masses of the particles, by the way, what I just said implies a measure of the energy density of the vacuum, which is, it is the substance of the vacuum, its energy density, which is producing, we think, the accelerated expansion of the universe. And that is symbolized by something called lambda, this energy density. So we know what the energy density on average of the universe is, and we also have a different estimate from particle physics instead of cosmology, from the properties of the Higgs boson, there is another estimate of the energy density of the vacuum. But these two estimates differ by 10 times, 10 times, 10 times, 10 times, 54, 56 times like that. So we're making an error of 56 sort of magnitude in comparing particle physics and cosmology. So there is something for you to understand in the future if you become a physicist. This is the standard models of macro and microcosmos clash with each other, maybe like Theseus and the Minotaur. Probably not, because what we think is that even if these two models are at the moment perfectly incompatible, our understanding of the large things and our understanding of the small things are completely incompatible, there will come in the future a moment in which someone, maybe one of you, will figure out how to get out of this problem, which is the biggest in science. And now that I'm looking at you carefully, I see several people under these circumstances, and that means I am almost through. So that was arguably the biggest problem in physics, and not arguably there are two other biggest problems for you to confront in the future. One of them is education below the university level. And let us compare, for instance, the education in this country with other countries, such as any Scandinavian country. An enormous difference between the education in those countries and the education in this country is that the teachers are very well paid and very respected members of the community. It's very good to be a teacher. Everybody would appreciate you. You would be very loved and do a very good job, and that is what they do. That's one difference. Now suppose we take a country such as Switzerland. In Switzerland, for the last mass shooting took place 21 years ago, and there has never been one in school. So something must be different, because in Switzerland practically everybody has a couple of guns at home, and yet look at the statistics. So there is a difference. And a good education, in my opinion, should be respectful of teachers and of nature, should be like and not unilaterally nationalistic or otherwise sectarian. Now, you may say, and you are right, that the United States is a country where everything is possible. Take, for instance, the Bronx Science School in New York. Children of that school got 7 Nobel Prizes in physics. So that must be a good school in some sense. If you think that getting the Nobel Prize in physics means that you have had a relatively good education, there are places not so far from here who manage to have a large fraction of their students get Nobel Prizes in physics. And the other big problem that you will confront, and it's not your fault, is global warming. And alas, this is a problem that my generation, the next generation, will leave to your generation to solve. And there's very little you can do except trying to do something. And I wish you good luck. And I think this is a good place for me to stop. Thank you. Oh, I leave you this to ponder. That was it.
Maybe there are some. Maybe you have some questions, perhaps. Well, anybody has a question? Hey. Anybody has a question or a comment to make? Well, upstairs there, yes.
Thank you very much for your talk. I thought it was wonderful. At the beginning, you mentioned about universities in the United States and universities in, for instance, France. And at CERN, of course, people from all over the world work. So when would you hire somebody from an American university? When would you hire somebody from France? Or what would one group be better at than the other group?
Well, the first occasion in which you can go to CERN is when you are still a young university student. For instance, I was there as a summer student, they are called, when I was 19 years old. That was my first knowledge of CERN. CERN has a policy that it can only hire people from its member states, of which United States is not part. However, that policy is not followed at all. If you have someone who is sufficiently good, he or she will be hired independent of his nationality. I don't know whether that was quite your question.
Not really.
This is because I have a bad cold and I hear very badly.
Apparently, I failed the test. So I was interested in, so you said that there are two different ways of learning. There are some people who are very, very, very good in physics and others who have room in their brain for learning other things, maybe because they're from a
No, I think you need the two things. Room in your brain and being very good at something. If there is no room in your brain, there is no use in you trying to put something new in it.
Got it. Thank
So
you.
a certain amount of healthy ignorance is good, I think. An overwhelming education in a subject so that you think that you know everything already appears not to be useful statistically if I compare French scientists with American scientists.
Thank you.
Any more questions or comments?
There's several.
Okay. Running. Where?
There, behind you. Oh, no longer?
Oh, well, there are so many.
Why does the Hadron Collider need to be so giant?
This is because you need a lot of energy to produce particles that you haven't yet discovered that have a very high mass. The energy must be sufficient to create a particle of a certain mass. Now, that means that as you go up in the particles that you are able to create, you have to go up in energy. And the thing is so gigantic because the magnetic fields, the strongest magnetic fields that you can create are insufficient to bend the particles into a circular collider. It's a limitation in the magnetic fields that you can produce to direct the particles around. There was another question here, maybe, I think. Yes.
How did they figure out how to do like the particle things? Did someone come up with like a theory and then they tested it on like a small scale, or did they build the huge one to test it?
It's very complicated. Sometimes particles are discovered that were not expected, and sometimes particles are discovered that everybody expected. And the difficulty is always for the experimentalists to find a way to make what you want to make and study it. There was a question here by this gentleman.
Oh, yeah.
So I have like two questions. The first one is so I picked up like from this lecture that creativity is what like makes people like successful. So do you think that like the schooling system in America is like suppressing creativity? Is that what like no?
Oh, there are very many ways to be successful. One is to be creative and manage to have success. Another one is to have very rich parents. There are various ways of reaching success.
And the second one is with the like atom collider, when they're making new elements, why, like if they have different properties, why haven't they like is there any that they found that are like useful, or are they just like kind of stupid, like just useless atoms?
Stupid atoms.
The fact that you're using a microphone is due to a 19th century physicist called Maxwell, who invented the laws of electricity and magnetism. The fact that you have learned all these things that you are quoting is due to the fact that you have internet, and internet works with a language that was invented at CERN for scientists to be able to communicate between different computers. If you have a touch screen in your telephone, where was the touch screen first developed? In a high energy physics laboratory. So everything that is done in these laboratories eventually is useful. There is no such thing as non-applied and applied science. There is applied science and not yet applied science. So basic research always results in the biggest conceivable progresses, which is not what it pursues. It's just a spin-off.
Is the collider can you use that to create like electricity in a cleaner way?
To create what?
Electricity or like
Electricity. No, you cannot make electricity. It spends a lot of electricity, but it doesn't make it. And to make electricity, there are ways based on particle physics. The most known one is the nuclear reactors that you have all around. And the future one is fusion. You can fuse nuclear atoms to produce electricity the way the sun does, but we are quite far from being able to do that. So the attempt to generate electricity in a clean, safe manner is one of the main goals of science, of course.
Yep.
In the collider, if the protons weren't sped up as much, would the collision would it create as many particles?
I couldn't hear it at all. You have a big voice, Luis. Can you repeat?
Yeah. In the collider, if the protons weren't sped up as much, would the collision create any new particles?
Yes, that's what they are meant to do. That's what they do. The protons in the collisions make things that were not there before. Some of them are new particles, such as the Higgs boson.
All right, so I noticed that the the particle accelerators are like under people's houses and stuff. So is it necessarily dangerous? Like, is the explosion like boom, or is it like a small little like it seems pretty dangerous to be messing around with.
The reason why you are asking me why they are built underground, for instance. They are built underground not because they are extremely radioactive and therefore dangerous. It's because it's much easier to build something flat underground than on the surface that goes like that, for instance, around Geneva. It's much cheaper to make a flat circle underground than on the surface. Moreover, on the surface, you probably have to buy the land, which makes it even more expensive. So it's a question of economic efficiency mainly to build these things always underground.
That's a question on that side. We should get more microphones.
Oh. So I know you mentioned the Higgs particle only lasts for a second, but what happens to it like after it, like, because it only lasts for like a little bit, but what happens to it afterwards?
What happens to what afterwards?
The Higgs particle? Or
These particles, the two protons that collide.
yes.
Where you have, they are made of smaller particles. The protons are made of 3 quarks. And one quark from one proton collides with another one from the other proton and makes new things. and the rest just go forward and also become other things, but have not collided. They just move along. So it's like in a collision of two bicycles. The cyclists get collide each other, but the bicycles continue, so to speak. There's a part of the object that collides with part of the other object, and then the rest of the object is still moving along.
The Higgs disappears. The Higgs particle is created for a very small amount of time, and then it decays into something else. So you cannot make a bag of Higgs particles. They all decay.
Oh, it decays.
They all decay immediately.
Okay.
Decays into what?
Into whatever. There are many channels to decay.
Okay, sure.
But the issue is that unfortunately we cannot make a little bag of Higgs particles to give to your mother.
Bucket of Higgs particle.
Another question here, Alvaro? Yes.
So I think you said in your presentation when that the Higgs boson decays, it actually produces, I think it was an electron and an anti-electron.
Sorry, I wasn't paying attention.
Okay.
Like you in class.
So in your presentation, I think you said when a Higgs particle decays, it produces an electron and an anti-electron. Now,
For instance, it can also do other things.
yeah, but like, would this be a reliable way to produce antimatter per se?
Oh, one of these particles,
It will be a very expensive way.
one of these particles is the anti-electron. There is also another accelerator at CERN called the anti-proton decelerator. Protons collide with other protons, and among other things, they make couples of protons and antiprotons. So you collect the antiprotons, and you study antimatter thanks to this collection. And you can also make antihydrogen by making positrons, which are the opposite of electrons, and you have an antihydrogen, which is made of an anti-electron and antiproton. And you can study, for instance, the very important question of whether or not matter and antimatter behave in precisely the same fashion. And this is being pursued with great enthusiasm also in various laboratories. So antimatter is something that we manage, but in very small amounts.
One of the unanswered questions is why is there matter and not antimatter in the universe? This is one of the questions that is still seeking for an answer. Any more questions or comments? Or you're all hungry? Yes.
Sorry. If the Higgs particle can become, if it decays and can become many different things, what determines what it becomes?
The mass of the object that it becomes. If the object is an electron, the probability that it becomes an electron is the square of the mass of the electron. If it is going to become a top quark, for instance, it's the square of the mass of the top quark. If it is to become a muon and anti-muon, it's the square of the mass of the muon. The muon is 220 times heavier than the electron, so the probability that a Higgs decays into two muons is 220 squared times more bigger than the probability that it becomes an electron and a positron. So it's the mass that determines the strength, or what's called the branching ratio, how often it decays in a certain way.
Any more questions? Comments? Yes.
Okay. So you said that the probability that the Higgs boson decays into a particle is based on the particle's mass, but all these particles, like electrons and positrons, have super low mass to the point where it's almost zero. So will that mean that, like, for the vast majority of collisions, the Higgs boson just doesn't decay into anything? It just disappears.
It decays more often into the heavier things, not in the lighter ones. If I was able to show In this transparency, I tried to answer your question. You see, it decays more often to taus because they are heavier than muons. And electrons are so light that they haven't been able to be measured yet, the decay into electrons. But the decays into all these 7 other particles or so have been studied, and they are proportional in amplitude. The probability is the square of the amplitude. They are proportional to the mass.
Okay, maybe we should leave it at that now. Well, let's thank our speaker again.